students, in the last lecture we discussed about a normal Zeeman effect and the difference between normal Zeeman effect and anomalous Zeeman effect. We also did an example of that, a singlet to singlet transition of electron, singlet state to singlet state transition, and that happens only in normal Zeeman effect, because in normal Zeeman effect the spin is always zero, S is always zero. But the explanation of anomalous Zeeman effect is hidden behind the spin factor. Here S has to be something, and we will consider the spin effect with respect to the orbital motion. Now because of the spin motion, what is the spin, that we will later consider that, but there should be some spin, and because of that spin the vector in vector addition or vector atom model, we see that the total angular momentum is actually the vector addition of orbital angular momentum and spin angular momentum. J is L plus S, right? And when the atom is placed in external magnetic field, this J start to presses around external magnetic field. Similarly, when we did the precision of orbital angular momentum around the magnetic field, and here in particularly there is a spin factor, and because of that vector addition, J start to presses around the external magnetic field, total angular momentum starts to presses around the external magnetic field direction. So then and this happens to be so specified that the projection of the total angular momentum takes some specific values, or take some kind of orientation, like Jz must be equal to mj h cut, and mj is magnetic total magnetic quantum number, the magnetic total quantum number. Then this Jz takes some specific values, and this is quite similar. We discussed that how L start to precess around the external magnetic field, and because of that precision, that precision came from the orbit magnetic moment, right? That when we apply external magnetic field on the atom, and then there is interaction between magnetic moment and external magnetic field, torque happens to be acting on this magnetic moment, and because of that torque, this magnetic moment changes its direction always, and that change happens to be only in direction wise. There is no magnetic moment magnitude increases or decreases. Because of this change in a magnetic moment direction, I'll start to presses around the external magnetic field, and that traces a coin, right? And the ratio of that mu L upon L came out to be E by 2m, right? So initially, if I don't consider S, and the J is actually equal to L, then if I apply the B external magnetic field, L start to presses around this external magnetic field, and mu L also start to presses around external magnetic field, and the ratio came out to be something like this, E by 2m as a constant value, right? But if I consider the spin factor, only the spin factor, then this ratio mu S by S is actually twice of this ratio, 2E by 2m. Now this is a complex structure, because if I add L and S through the vector addition, then if L is in this direction, S is in this direction, or S is in this direction, if I add them, then J has a particular direction this, and when I apply the external magnetic field, J start to presses around the external magnetic field, and it traces a coin. Now these ratio are not equal, so this is a problem. Because these ratio are not equal, then mu S, mu L and mu S, and the mu total mu is not exactly anti-parallel to J. J has this direction, and mu J is not anti-parallel to this. The direction of mu J is something like this, because mu L is in this direction, mu S is in this direction, and both of these start to presses around this mu J. This also start to presses around mu J. So the ratio was initially J is in this direction, and this is in this direction, and these are presses around something like this. So we need to determine some Landesi factor here, and that leniency factor is very much important in anomalous Zeeman effect. Okay, so let's determine the leniency factor. And how do we determine that leniency factor?